let's just get into it, guys. Okay, so have you ever listened to like a toddler counting? As soon as they start learning how to count, they usually start from 1. So you'll hear them say 1, 2, 3, etc. And that's how counting first started, I guess. And the first type of number system that ever probably existed was the natural set of natural numbers, right? And then eventually they realized, well, hey, zeros in there as well, so we got to pop that in. And of course, you know, you had your negative numbers as well, so they found their pair, so plus and minus of all those natural numbers in addition to 0, and they put this in a box and they called it the set of integers, right? A set of integers. Now it's kind of nice to recall what the symbols look like, because they do pop up on exam papers and a lot of students do not know what they mean. So natural numbers tends to be represented by an N, and you'll see integers represented by the letter Z. I like to write a cross in between, but usually you'll sometimes see it looking like this. All right. So from natural numbers into integers, what happened is that, you know, everything was just like perfect. You had whole numbers. You didn't have a piece of cake cut in half. Okay, so then they realized, hey, they need to extend the number system to allow for fractions and stuff like that. So whenever you have like values like fractions like a half and plus or minus 3/5 and stuff like that, these types of numbers, except of course for the case scenario where you have the denominator being equal to 0, you would have called these types of numbers, if you guys can remember, they're called rational numbers, right? So anytime you hear the word rational, think of like fractions, fraction type numbers, right? All fraction type numbers that has a numerator and a denominator, once the denominator is not 0, it's rational, right? These are usually represented by the letter Q as well if you wanted a symbol. Not so popular on past papers though, but these are very popular. All right, and moving along, getting a little bit closer into what complex numbers is all about is what we're going to learn about now. So we had natural numbers, then people realized there's positive and negatives, you had integers, and then there's parts of whole numbers such as rational numbers, you know, fractions and stuff like that. After that realization, I don't know, maybe they were learning to build houses and stuff like squares. Imagine that's like the floor plan of a house, you know, and one side was X and the other side was X, so therefore the area of this square floor plan would be X multiplied by X, which gives us X squared, if you guys can remember your basic rules of algebra. Now, what if they said they know the value of the square footage and it was like, I don't know, 210 maybe? Then what's the value of X? Well, you know, if you're squaring a number and you want to find the value of that number, you have to do the reverse, or the inverse rather. And the inverse of squaring a number is to find the square root. So therefore, X, if the area is 210, X would simply be the square root of 210. And I'm guessing that when they saw like values like that, they were blown away, because then they had numbers and answers and solutions that looked like this, etc. None of these values seem to fit into any of these number type systems. So what they had to do was to extend the number systems that they had to include these types of values, where you have like stuff like X squared being equal to 2, that produces numbers that look like, you know, 14.49, pretty much like positive and negative decimals, you know, square roots of numbers and stuff like that. All those types of numbers are said to be real. So pretty much any number that exists, whether it be 0, whether it's positive, whether it's negative, you know, once it produces some type of like decimal form value, it's said to be a real number. Now, real numbers can also be whole numbers as well. They can also be fractions. Pretty much once they fall into any of these above categories, they're all considered real numbers. So you can say natural numbers, integers, rational numbers, they're all subsets of real numbers, right? And very, very important, the symbol for real numbers look like this. It's the letter R, and they tend to double up the beginning of it a lot. All right, so then we had the real numbers and life was going really, really good, you know, and then boom, this happened. They found a situation where x squared was no longer a positive value like 2. It was something like -1. What were they going to do? Well, I'll tell you what they did. What they did was they introduced something called imaginary numbers, okay? They introduced something called the imaginary number system, represented by the letter, the imaginary unit, rather. They don't really have they don't really call it I, but the imaginary unit is known as I, and it has a value of the square root of -1. Sometimes people like to learn it as I squared is equal to -1. And that was done, I guess, because they just do not like to see the negative sign popping up, to eliminate it in a way. So for example, back to this example in red here. Let's just say that, x squared was indeed equal to -1. All right, and you can see from here, -1 can be replaced by I squared. Therefore, we can rewrite this as follows. -1 can be replaced by I squared. And there you go. You have a nice, clean, positive, if you want to say that. You have a nice, clean letter that eliminates, that negative sign in front, but it's there. And you get to call it imaginary because it's not really it's not a real number, right? It doesn't belong to any one of the categories of natural, integers, rational. It doesn't belong anywhere, right? So imaginary numbers are numbers which have some component of I, where I has the value of the square root of -1. Like I said, a lot of students prefer to remember it as I squared is equal to -1. Now, you may be asking yourself at this point, when's this story going to end? This is like a really, really long story. Well, we've actually reached the end. Woo! Okay, so back to the beginning. What were we talking about again? Yes, we were talking about complex numbers, right? So complex numbers, pretty much in a nutshell, is denoted by the symbol C, okay? And it's a type of number system that was introduced when real and imaginary numbers came into play. So a complex number is like a two-part system, all right? It belongs to, it can be plotted on like the Cartesian plane and stuff like that, but we'll get into that later. But for now, a complex number takes the special form of Z, and this is a different Z from the set of integers, mind you. It takes a special form of Z is equal to X plus IY. Simple as that. I know it looks complicated, but all you need to remember is that a complex number system comprises of two parts. The first part, the X, is the real part of the system, and the second part, that IY part, is called the imaginary part of the number system. Okay? And why do you think it's called the imaginary part? 2 seconds, guess. That's correct, because of that component of the I being present there. Because anytime you see that letter I popping up into number systems, that's because we have some sort of imaginary component. So straight off the bat, what happens is that it's very easy up front to recognize a complex number. It has that two-part component present. Let me give you some examples of a couple of complex numbers, so I'll show you how easy it really is. An example of a complex number is z is equal to 3 plus 2i. Okay, so you can see that it has two parts. It has a real part here. Okay, so the real part is 3, and it has the imaginary part, and the imaginary part is 2. Please take note. Let me just put that over here, and let me erase this over here so that you guys can understand better that x is the real part and that y is the imaginary part and not the entire iy. Okay, please take note that the imaginary part is only the coefficient of I. Okay, so it's not the entire thing. So if somebody were to ask you in this example over here, hey, what's the imaginary part of z, where z is equal to 3 plus 2i, do not say the imaginary part is 2i. The imaginary part is 2. Okay, that's how you will answer them. Let me give you another example. So let me just scroll down here. It's not that bad. Okay, let's look at another example. Okay, so by examples, this is going to be like really easy. Sometimes they do not state that z is equal to. They'll just give you the complex number up front. For example, they can give you, like 7 minus 5i. And they can ask you to state the real part and the imaginary parts. Okay, so what are the real and imaginary parts of this complex number? Up front, it's a two-part component, and you can recognize that I being present. So one, that's how you recognize a complex number. It has that I, and it's a two-part component, right? And the real part is the one that does not have the I. The real part is just the number 7. And of course, the imaginary part is only the coefficient of I. Now, in this case, we can see that the coefficient of I includes a negative number. So we must include that sign of negative, right? So it's negative 5, not positive 5. If you were to rewrite this, you can rewrite it as 7 plus negative 5i. Okay, just so you can see it. Gave you guys a visual there. Now, of course, like this is too simple. It does get a little more tricky. I'll show you guys another case scenario. Let me just scroll up here. Here are some more examples. For example, in the future, when you guys will be learning about like polar forms and stuff like that, you'll see a lot of trigs involved. It's present, but you don't have to actually do trigs, so no fear. Okay, so like sometimes you can see stuff like this. You have a complex number that looks like negative 4 x squared plus like 2x plus ai. Now, once again, it's easy to recognize something is a complex number. First of all, it's generally question 1 on your past paper. And second of all, there's always going to be I present. Okay? Always. If it's not there, you're not dealing with a complex number. Right? And it's going to have a two-part component. In this place, in this question here, the real part is 4x squared, the entire thing. Okay? Because x has a value that's unknown to us. So we have to consider it as being real. And I, definitively, we know I is imaginary. So therefore, the coefficient of I here would be the imaginary part. And so on. Okay? So guys, I hope you guys understand the purpose and the reason behind why complex numbers were created to begin with. It's because we needed to extend the number system to allow for new values that just did not fit anymore into our number system. And a complex number is very simple. It's complex. That's funny. A complex number is very simple. It's complex. A complex number is not that bad to recognize. It always has that I present. And just always remember that the imaginary part is the coefficient of I. Okay, guys, so that's enough story time. That's a big enough introduction for what a complex number looks like and what it is. So moving on, let's get into it. Okay, so up next we will be moving on to addition of complex numbers. Okay, so just like with any number system, if you have basic numbers, -2 plus 5, you have -2 multiplied by 5, you have -2 divided by 5, you got to learn to do the 4 basic operations with any number system. So similarly, when it comes to complex numbers, you got to learn how to add, subtract, multiply, and divide them. Now, because they have like a 2-part component, it can be a bit tricky for certain operations. The easiest one is addition and subtraction. I'll show you how simple it is by example. For example, let's just say we have a complex number, Z1, 3 plus 2i, and we have another one, Z2 being equal to 5 plus 4i. And then they're asking you, well, add the two numbers. Add the two complex numbers. How are you going to do that? Well, as with any addition, you write down what you have. It's a substitution. Z1 is 3 plus 2i, and Z2 is simply 5 plus 4i. You'd simply rearrange your like terms and whatnot, and you will end up getting 3 plus 5 gives you positive 8, and positive 2i plus 4i. You think of it like in terms of algebra, 4 plus 2 gives us positive 6i. So the sum of these two complex numbers gives us simply 8 plus 6i. So you usually end up with another complex number as an answer, right? So that's how easy it is to add two complex numbers. You just pretty much treat it like an algebraic expression, and you just simplify. Okay, same thing goes if you had to subtract these complex numbers. So if I were to do subtraction, okay, and in my second example, what if I said to find Z1 subtract Z2? What is our final solution going to look like? Well, you're going to have 3 plus 2i. Now, because it's a subtraction, you have to recall that whenever you are subtracting something that has multiple terms in it, you're going to have sign changes. So I'm going to actually have to put Z2 within brackets. And as simple as subtraction can be, these are the small things that make students lose marks. A lot of people would have not put this in bracket. And what would have happened is that, you would have only distributed that negative sign over the 5, and you would have unfortunately forgotten to do it with the 4. But because of the presence of those brackets, you will actually have 3 minus 5 plus 2i minus 4i. So your final complex number looks like -2 minus 2i. Okay, so little important key elements such as introducing your brackets when you know it belongs there are essential in getting your full marks. And pretty much that's it. That's it for how difficult addition and subtraction of complex numbers can be. It's really nice. I told you would enjoy complex numbers. It's a beautiful topic. So next up, we're going to get into some multiplication. Okay, so we have two types of multiplication which can actually take place. Like I always like to tell students, when you're doing complex numbers, think of it in terms of algebra. It is pretty much algebra. For example, let's consider that you had a complex number z being equal to 3 minus 2i, okay? And for multiplication, they want to know, well, hey, what's the value of 3z? Well, 3z will simply be equal to 3, open brackets, because you have to remember that distribution rule, and you simply would, like as in algebra, you would distribute that 3 over each of those terms, and you would end up getting 3 3s are 9 minus 3 2s are 6i. Very, very simple, very straightforward. Now, that's if you multiply a complex number by a real number, right? Just a constant like this. Now, what happens, so you'll see it denoted a lot of the times, like this type of multiplication is like if you're multiplying a complex number by some kind of constant called lambda. So lambda z. This is one of the first rules in multiplication of a complex number. Okay, now the other rule is when you're multiplying two complex numbers. This is the one we want to get into. When you have one complex number that looks like a plus bi multiplied by another complex number that looks like the form c plus di. Okay, now the reason I have different variables present is obviously because I want to differentiate the first complex number from the second one. Had I used the same variables a and b, then it would have been the same number, okay? Not that you cannot multiply two, you cannot, that would essentially be squaring a complex number if you multiply it by itself, okay? But anywho's, how essentially would we go ahead and multiply two complex numbers? Well, I'll give you guys a chance to guess. Think about it. If I just mentioned to you guys, think in terms of algebra, think in terms of brackets. What do you do with brackets? They look very familiar. And if you're thinking distributing or expanding your brackets, you are correct, right? So you just go ahead and you distribute, or you, like some students like to say, you expand your brackets, and some people like to say that they use the FOIL method to expand your brackets. However you do it, and whatever your complex number looks like, this is how you'll go ahead. I'll go ahead and use arbitrary values of a and b and c plus di, okay? I could have used numbers like -3 and 5, but it's fine. So here goes. How do we multiply two complex numbers? Like this. So first of all, using the FOIL method, you'll multiply a by c. So we will get ac. Then we'll also multiply, so that's these bottoms here. And then you multiply a by di. That's a di. Now, the way in which people multiply could be different. It really doesn't matter once you go ahead and do it correctly, okay? Then you can multiply bi by c. I want to put this in an arranged manner, so you'll get bci. Make sure you always write that complex component, or the i's rather, last, okay? And then finally, you would end up getting bi multiplied by di. Please remember to account for those signs in between in case they were negative, okay? So that's positive bi. Let's take that to the side. Positive bi multiplied by positive di. Let me eliminate this plus sign here. How do we multiply these? So you'll get b di squared. Now, doesn't that look familiar? What do you guys remember about I squared? Do you remember that I squared is equal to -1? If you do, give yourselves a clap. So I squared is actually equal to -1. And because I squared is equal to -1, we can actually simply replace, every time we see I squared, we can replace it with -1. So over here, this is actually -1 multiplied by BD, which just gives us -BD. So this sign changes to -BD. B, D. And remember, at the end of the day, whether you are performing addition, subtraction, multiplication, or division, you are going to get some type of complex number at the end. And this solution has essentially 4 terms there. So what you want to do is just take your time and you want to go ahead and you want to rearrange these in such a manner where you have everything that's real, or everything that looks seemingly real. You want to bring it together. A lot of students would have forgotten to bring that negative BD up top. Remember, when you're moving a term around, you have to move the sign that is in front of it as well. And then we're going to factorize out that I to get AD plus BCI. Did you all see what I did there? I just simply grouped together the two like terms in terms of I, and I factorized the I outside. So now what we have is we can see clearly that this is the real part, and this, excluding the I, is the imaginary part. And here we have the product of Z1 multiplied by Z2. It's a very huge complex looking number, but it is correct. And this is the method you would use time and time again to multiply two complex numbers. It's not hard. Form 5, you've been doing it since you were in Form 4 and you learned how to use the distributive rule for when you're using the FOIL method, to find quadratics and stuff like that. It's just that, essentially it wasn't involving like complex numbers, but you understand the method behind it. So this shouldn't be too bad.